Thank you very much. I indeed will have to finish what we have discussed. In the second lecture, it won't take much time. Let me just recall what we have done. By the end, we've been looking at quantum Hall setup, one-channel setup, which will exhibit Aronoff-Bohm oscillations. Well, to this end, we will need to make a loop, which means that we need to split these channels. So we use two beam splitters to arrange the loops. Then we put flux in the loop, and we get conductance, which will depend not only on characteristics of the beam splitters. It will depend on phase shifts accumulated in the loop. It will be dynamical phase and geometric phase, which would result in Aronoff-Bohm effect. And let's see, we will look at the trajectories and understood that for some pairs, dynamical phase enters expression. So the effect depends on dynamical phase. And that would give rise to oscillations which are periodic with a period 2. Flux quantum. While there are some special pairs of trajectories which differ by the direction of the loop, clockwise or counterclockwise. And for these specific trajectories, dynamical phase cancels. All right? Period changes for these trajectories. Good. We express this mathematically. We have found conductance. It's a plot. So for individual realizations at given dynamical phase, there are spectacular oscillations, Aronoff-Bohm effect. Right. If you want averages over dynamical phases, then the result will be periodic with a period which is 2 times small. So there are large period which you cannot see unless you average over dynamical phases, and small period which you had when you do. Good. It's all abstract, so let me switch to experiment immediately. Was classic experiments. It's not about classical physics, it was about quantum mechanics. It was where one of the pioneering experiments which have shown that electrons in condensed matter are quantum objects. Right. So that has happened quite some time ago, but, well, I have been already born by that time. Good. First experiment. It is perhaps important for understanding that this has happened yet in the time of Cold War. So there was a competition between Soviet teams and American teams. Eventually, in this particular area, competition was quite friendly. And, it's not typical for present times or present situation. People really care about each other's results. That was one of the positive setbacks of Cold War. Good. So there was an experiment by Soviet team. What they did. First of all, you see the oscillations, and you understand it's Aronoff-Bohm oscillations. Then let me describe the system. It was, I would say, stone age of nanotechnology. But they make use of the fact that some crystals grow in the form of very, very thin whiskers. Such a whisker could have several fractions of micron in diameter and can extend long. Good. What they did, they put some metal, I believe tin, around the whisker, forming a cylinder. They put magnetic field in the direction of cylinder axis. And they put also a couple of contacts. They have measured the resistance of the structure as a function of magnetic field. Let us see. First of all, the modulation is small with respect to the total resistance. We haven't discussed it yet, but it's just because that the cylinder was rather big, metallic, so there were many transport channels in this cylinder, and eventually only one single transport channel is responsible to Aronoff-Bohm fluctuations. Okay, so they saw in resistance the effect of one channel roughly. Good. So, control question. Although if you read carefully, you know the answer. What was the period of these oscillations? Was it long period or short period? That's important. Please give time to think. Look, you know, right answer is 50% of probability. People in quantum computing kind of sometimes dream of such fidelity. So who dares?
I don't remember who is short, who is long, but we see period after average.
Okay. Indeed, it's shorter period. So can you explain why do you see period after averaging?
No, in my explanation there is some in the temperature and it's
No, electrons are finite temperature, but why would it matter?
different electrons have different vectors and they have different phase shifts.
Electrons, they do have different phase shifts, you're right. But that doesn't come because of temperature. It just comes from the fact that the sample is rather big. As we see, it encompasses lots of quantum channels. And each quantum channel kind of has its own dynamical phase. We see in the sum. So we can only see the effect which is averaged over dynamical phases. Fine? So it's short period. It's called weak localization. We don't talk about this, but well, it's clear that this is an effect of averaging, which surprisingly doesn't vanish as the oscillations of the first kind. Good. All right. Not that it was precisely a race, but like space race. But in 4 years, Americans have made something very similar, but in a different setup with high technology, with different result. Right. What did they make? They didn't make a long cylinder. Just made a loop with a size of like 100, what was it? Like 1,000 nanometers more like this. But it was very thin. So, in fact, what they see, if I remember correctly, there was an effect of like only 30 channels. They measure, again, the resistance of the structure. A two-point measurement in this case between the leads. Right, and they got such patterns which, well, they call it grass. I don't know which analogy you have. So it was something which apparently oscillates, but it does it in very irregular fashion. In order to see periodicity, one has to make a Fourier analysis of this with respect to magnetic field. There is a result of Fourier analysis, and the peaks correspond to kind of most probable periods of oscillation. So one can see main period, one can see also double signal, kind of high harmonics. Good. Again, the answer is written at the slide. But okay, were these oscillations with short period or long period?
By the previous argument, if they had not a lot of channels here, then they maybe not average out, so we should see the long period.
Yeah.
But it's also written there, so it's
Yeah, it's also comes from the fact that the signal is much more random than in the previous experiment, right? One can see all this, the oscillations are not regular. It looks like you have oscillations which are shifted, and the shift is random phase, in fact. All right, these two experiments were kind of opening of all quantum transmit experiments. These two experiments have proved finally that electrons in solid state are waves, subject to a Aronoff-Bohm effect. Good. Any questions about subject of interference? Since I will switch to other topics. Yes.
sorry, I missed the point about the dynamical phase and the Aronoff-Bohm phase. Okay, when does why one constant and not the other?
Once again, there are many ways electrons can propagate through the structure. And the interference signal always comes from pairs of trajectories. There are pairs of trajectories which are not sensitive to Aronoff-Bohm effect at all. There are pairs which are sensitive. Let's see. For instance, this pair. And the interference signal in this case includes dynamical phase. Why is it so? Because passes taken by these trajectories are different. Okay, that includes dynamical phase. And it has a certain period with respect to magnetic flux. One could say, well, it's simple. One could, quickly conclude that the effect, Aronoff-Bohm effect, vanishes upon averaging over dynamical phase. This conclusion is wrong. One needs to understand that there are pairs of trajectories which pass precisely same pieces of the nanostructure, but do this in opposite way. Interference of these pairs allows to cancel dynamical phase and completely concentrate on an Aronoff-Bohm effect. Right, and then depending on experimental conditions, you either see the average, so the signal from these pairs of trajectories only, or you see also random signal. Your question, please.
Are these paths time reversal paths?
reversal. Define reversal.
Are these two paths time reversal paths?
With respect to each other.
I thought that this is related to the Euler-Aronov Spivak theorem.
Spivak.
Well,
Let's go step by step. These two passes are not time reversed with respect to each other. If it were, electron would go in opposite direction for this path. It still does it in the same direction. However, the direction of the loop, the direction in which it covers the loop inside the structure, is opposite. Okay? So it's not precise reversibility, it's reversed with respect to a loop. Does it answer your question?
yes.
All right.
For example, in the E case, the lower case, it includes one plus I, and in the other case, no plus I.
Now it includes the flux both times. So let us see. Perhaps it's just visual problem. Does it answer your question? So both passes make a loop. D does it in, let's see how clock goes, in clockwise direction. And this does it in counterclockwise direction.
It's the same dynamical phase, but opposite.
Yeah. Fine. More questions about Aronov-Bohm, about interference in general? Yes?
So you said that whether we have the averages of these trajectories or the others depending on the experiments in detail?
Yes, precisely. So for a long sample, for a big number of channels, you most likely cancel the random effect of the phases. If you make smaller sample, there's American technology, then you kind of you have a chance to see random oscillations which depend on dynamical phase. There was also interesting experiment by that time when they tried to push electric field into a metal to change dynamical phase and to see its manifestation in a Aronov-Bohm effect. It was kind of tediously difficult. Somebody knows why? That's because of screening. Metals tend to screen magnetic field. So they had to go for a very, very bad metal. And right, in that case, they could see some effect of interference. They just apply gate to metal, and it worked. For metals, it's pretty hard. This structure is made from conducting semiconductors, interdimensional gas. It's a semiconducting structure. This effect is more pronounced. It gives to the gate. Yes?
So if I understand it right, in the example with a metal cylinder, or also this just a tiny loop that US team used, actually along the path that the electrons take, there is some magnetic field, so the rotation of A does not vanish. So actually when I average, I cannot get rid of the dynamic phase. Is this right? So I will always get some phase that is connected to the magnetic.
No, wait. You just have many contributions of pairs at previous slide. Let's see. So there is a one pair with a certain value of dynamical phase. Plus you have another pair, you have zillion of these pairs, they come all with random phases, so the effect vanishes.
But isn't this all under the assumption that the rotation of A vanishes along the path of the electrons?
Rotation of which quantity?
The vector potential, so it should be a D field.
That's for sure. Whatever the geometry, the relative phase is given by the flux enclosed by the trajectory. It's also so that the cylinder has finite thickness, which means that the fluxes enclosed by different trajectories, they differ a little bit. But that's kind of a very small effect in this case. One can disregard it safely. All right? No more questions? Then I will go with the next lecture. Oh, let's see. Next lecture. Usually I started with Andreev scattering. But in this case, my usual problem is that I don't come to spin scattering. So let's make it differently this time. Right, so I will start with spin part. I must confess I like spins less than superconductivity. That's again yet another reason to start with this. Right, so we've been talking about quantum transport, scattering the waves. We didn't take into account by that time that electrons have spin. So in fact, wave function of an electron has two components, with spin up, spin down. These components can kind of change from point to point. Right, one can define actually operator of spin in the basis of these functions, which can be made from three Pauli matrices. It's like a geometric vector, in more exact terms, pseudo-vector, with three components. Right. What could make spin effects visible? Usually they are not visible. Usually it's safe to assume that all electrons are spin degenerate and are not spin active thereby. One can polarize electrons. One can apply external magnetic field. Well, it will also change orbital properties of electron motion. So we can forget about this for time being. It affects its spin. Another way, just to use ferromagnets as contacts, as electrodes of the nanostructure. Right? In this case, in a ferromagnet, electrons with different spins have different velocities, have different densities of states, are very different. That's the way to make spin planes a role. And the third factor, which is usually small but can become important, is spin-orbit interaction. It is this orbital motion of electron talks to spin. All right? So it is, yeah, I will talk more about this. Good. Simple message, electrons have spin, and we'll try to understand quickly at very surface level what does it mean in the context of quantum transport. Good. Let us first start with a simple example. I would say it's even below master level. It's about Zeeman splitting. All right? So let's have electrons with a parabolic spectrum. P squared divided by 2m. Let us apply magnetic spin, a magnetic field, and let us disregard orbital effects, right? Then there is a term in Hamiltonian which takes vector of magnetic field and activates corresponding Pauli matrix, all right? So, in this case, it's healthy to choose spin quantization axis along the magnetic field. And we have two species of electrons with spin up, spin down. And the spectra are shifted. Here's the shift. Good. So, if now I plot the spectra, two parabolas shifted with respect to each other, spin down, spin up. And if I look at certain energy, let me take for instance this one, I see that electrons with spin up and spin down are very different. Moreover, at some energies there are no electrons with spin up at all, so the carriers are polarized. Good. That's guess one of the simplest models about spins. Nevertheless, it's not that bad to describe real ferromagnets. So you just have doubling of the spectrum. There are two spectra for electrons with spin up and electrons with spin down, which is, by the way, a pretty classical picture, but we will discuss this. Fine. Let us get back to the lecture number 1. Let us recall the picture of adiabatic quantum transport. So, we have a long channel, and we have a constriction in this channel, right? The kinetic energy in the constriction becomes potential energy. So, as we remember, the constriction works as a barrier for an electron, for a certain transport mode. Right? If there is no spin effects, then we have either open or closed channel for both spin directions. But if we manage to put magnetic field inside, the potential barriers for spin up, sorry for my drawing, and spin down, just different. So in this situation at Fermi energy, the channel for spin up is closed, while electrons with spin down can freely pass the structure. Good. Which I want to illustrate with a picture. It's rather bad rendering. But believe me, original picture is so beautiful that you would never believe it's an experimental picture. But it is. All right, what does it show? It shows the conductance of quantum point contact versus voltage. So this exhibits steps. And different curves correspond to different magnetic fields. So you see that instead of a single step with a value of conductance quantum, in high magnetic fields, we have steps at half-integer values of conductance quantum. What does it mean? It means here only electrons with spin down can go through the structure, while electrons with spin up are pretty much efficiently reflected. So the device works as spin filter. So one runs electric current through, applies voltage. Voltage doesn't know anything about the spin. As an output, you have current of spin, not only electric current, but current of spin transfer from one part of the structure to another one. That's interesting. That's a subject of science which is called spintronics. And we look at it in the context of quantum transport. Everything's clear in the slide? Yep, okay.
So on the last graph, for the b equals 0 curve, the right part is pretty smooth, but on the left part there is a smooth.
Yeah, okay, that's 0.7 anomaly. There's been many posters, there will be many posters 0.7. I kind of always feel ashamed. This feature is also pretty clearly visible on the first curve I showed, the first ever experiment with quantum point contact. And it's kind of clearly seen for most experiments with quantum point contacts. All right. It became clear very soon, in particular from this experiment, that it has something to do with spin, right? One sees that upon application of magnetic field, first this structure becomes more pronounced, and only then there is a formation of two spin plateaus. It's also clear that it's many-body effect, because nothing is a picture of free electrons would provide an explanation for this. However, I must confess that at least in my taste, the anomaly remains unexplained. There are many different attempts of different level of complexity and, how shall I say, reasonability to explain the anomaly. On my taste, it kind of some work for you. Please explain. Good. More questions? Answers. Let us see. So it's a kind of a simple but very clear manifestation. So let me talk a little bit about theory. Let me talk about spin-orbit interaction. I'm almost sure that you have heard about this in many setups expressed in very many different words. Let's see how would I express it. For me, it's a relativistic effect, and it is manifestation of the fact that moving electron feels electric field as a magnetic field. So, in fact, Hamiltonian for spin in this case becomes, well, the same set of Pauli matrices times effective magnetic field, which is vector product of electric field times velocity, and in the system of units, which is not legal in this republic, I put C here. Okay, So there's some French proportionality coefficient in front of this. Good. So it means that an electron which moves with velocity v feels electric field as magnetic field. Fine. That makes it small in most of the metals, most of the conductors. If one considers the effect of spin orbit onto functions in a metal without scattering, one does not see much. This is due to the effect which is called Kramer's degeneracy. A spin orbit interaction by itself does not break time reversibility. So any pair of levels formed in the metal can be obtained by time reversal, which means that the levels remain degenerate despite the fact that they have some spin structure. So it doesn't do much. However, if one looks at scattering of electrons in metal, like we do, we have nanostructures, there is possibility to change spin in course of the scattering. Right. If you do it many times for many electrons, that randomizes spins. Is it clear? So different scattering processes are different. Electron hits impurity. If it goes to the left, it tries to polarize upwards. If it goes to the right, it tries to be polarized downwards. That's why it forgets initial direction of spin. But since the interaction is small, usually it takes many scatterings to come to a single spin flip event. Like in aluminum with the usual impurities, it would be like 10 to the 4 scatterings at impurities to achieve the single spin flip event. All right, that's what we want to know about spin-orbit interaction in normal metal. Who wants to know more? Nobody. Good. Perfect. Let us see. Let me go a little bit down. Let me talk about general situation. Let me understand what does spin change in scattering approach. Right. Actually, at formal level, not much. Instead of scattering matrix, which dependent on two-channel indices, we have scattering matrix which also takes into account initial spins. So we ascribe spin index. These spin indices can be the same. In this case, we just have different scattering for two spin spaces. Or it can be different. In this case, we describe the situation of spin flip. Right? So generally, we can kind of put the spin dependence into vector part of scattering matrix, which comes with Pauli matrices. Time reversibility is important here. There are two ultimate cases. There are two contributions to this scattering matrix. One comes from spin orbit. And spin orbit in general does not change if you just apply spin orbit, the material remains time reversal, right? That implies the following. That implies that this matrix is asymmetric in indices. In particular, there is some strange rule which seems to be dogmatic, to be too dogmatic to be true. Nevertheless, there is no spin flip if the scattering is within the same channel, owing to asymmetry of this matrix. If the channel indices are the same, it's 0. Right, and although there were many experimental attempts to kind of circumvent this rule, some of them have been successful for a couple of years. Good. In magnetic field, the symmetry is the same, but in this case, everything is polarized along the magnetic field, and there is no spin flip. There are different scatterings for different spin directions. Okay, that's general scattering matrix in the presence of spin. Yep.
Here when you talk about the time reversibility, what it implies, what do you mean in a magnetic field? Because you don't have time reversibility.
If this part, so that's not the same as here and here, I'm sorry. This part comes from spin orbit.
Okay.
It's asymmetric. This part comes from effect of magnetic field. And this is symmetric, right? It's sure, because if you change direction of time, you also change the direction of magnetic field.
Okay.
Right. Let me recall what we had in quantum point contact. We made a spin filter. We know how to produce spin current if we apply voltage. That's again, there's a whole science which is called spintronics, which studies the production of spin currents and their use. So let me write a short formula. What does this mean? How many spin currents do we have in the bulk? Just look at this formula. Yes. So there are 3 directions, geometrical directions, and there are 3 directions in spin space. So there is a variety of spin currents. Great. So spin currents can serve if we forget about spin orbit interaction. Right. If can we forget about spin orbit interaction? Looks like we cannot. However, let us recognize that usually it's weak. It requires many scatterers, many scatterings. And electrons propagate for a distance between these scatterings. There is a finite spin relaxation time, which means that conservation persists upon a certain length. The conservation spin current persists at the distances of the rotor of the spin flip length. Right, which makes sense to look at spin currents, to look at these responses on voltages. Again, spin filter, we already know, and we can have this value, another thing how to measure it experimentally. There's no spin-ometer to my knowledge. One has to do something else. Did I say everything? Right, perhaps I need to explain this thing. In non-ferromagnetic metals, the histories of all spins are the same. That's why all components of spin current are conserved. if one considers ferromagnet, then only a component along the quantization axis of the ferromagnet is conserved. Perpendicular components vanish. Why is it so? Because electrons, in this case, they have very different history. Like different, they feel different velocities, they feel different spectrum. So any coherence between electrons of different spins vanishes. So it's strange filtering as well. Only one component is conserved. And all other components, they vanish very quickly in the ferromagnet. Good. Okay. How to detect spin? Yeah.
Do you suppose that the velocity and the Pauli matrix is convoluted?
They do in this case.
Okay. And conserving.
Otherwise, I would have to symmetrize the expression.
And conserving the current, so that means the spin current or the current of the total angular momentum.
The structure is mounted. There is no conservation of angular momentum.
Okay.
But there is a conservation of spin, again, at some distances only. Right. Let me tell you something which you might know, but which might sound trivial, but in fact it's very interesting. There's not only spin current. Fortunately, we also have spin voltage. What is this? It's called spin accumulation. If one talks about two spin directions, one can easily imagine a situation where chemical potentials are different for spins up and spins down, right? Non-equilibrium situation. Okay, we have excess of spin, we have spin accumulation. Let us now recall that spin is a vector quantity. So that gives only that component of this quantity. There can be also x and y component. So, in fact, as a result of spin current, one can accumulate spin. So we just take spin current, put it in a certain reservoir, and write with some chance, if spin flips in this reservoir are not very small, one accumulates spin in the same direction. Okay, then one comes again with a spin filter. If electrons are polarized, they produce different currents. So the spin accumulation can be also detected with a spin filter. That's how most experiments are done. One needs another spin-active nanostructure to measure spin current produced by first nanostructure. So one can now let us understand that this implies that there's something in this business except the electric conductance. Electric conductance is a proportionality coefficient between electric current and electric voltage. In our case, we can have current and spin currents. We can have voltage and three directions of spin accumulation. And all these quantities are related within linear relations. Let me first consider very simple situation when we have electrons only with a certain spin direction. In this case, we can't forget about the fact that that spin is quantum mechanical quantity. We just say there are two species of electrons, each has its own history. Then we can take two scattering matrices, two transmission coefficients which depend on spin. We can figure out the currents of electrons with spin up, electrons with spin down, right? Then we can make equations. That's for electric current, and it feels spin accumulation in this direction with a coefficient which depends on the difference between transmission coefficients with different spin. All right, so that is detection of spin accumulation. The spin current, again, it depends on spin accumulation as well and on polarization properties of the contact. Okay. That's pretty comprehensive but boring. Let's make it fancy. Let's make it quantum mechanical. And in this case, it's achieved in very simple manner. Let's just turn the quantization axis a bit and allow for arbitrary spin directions. What do we have to add? I just concentrate on the place on the terms which we want to add. In this case, there are spin currents in the directions perpendicular to polarization direction. These spin currents, if we concentrate on interface between ferromagnet and normal current, normal metal, these currents will vanish in ferromagnet. But they would be in normal metal, right? They would be normal metal, and they should be related somehow to the polarization. So we have another coefficient of dimension conductance, which characterizes spin properties of the interface of the nanostructure. This is called mixing conductance. That coefficients can be computed with scattering theory. Look at this expression. If these spins are the same, it would just give me conductance of a certain spin direction. That would be transmission coefficient. Here it's a Landauer formula for this crazy quantity. Amplitudes are not the same, so it's not transmission coefficient. All right, this is mixing conductance, which in fact one can say is a simple quantum mechanical effect upon spin scattering. Okay, that was it about spin. Questions? All right, I'd better start with superconductivity. Let's see. Let me talk about superconductivity. That was a discovery made before the discovery of quantum point contact. Also in a different city, not in Delft, for some strange reasons. It's been discovered in Leiden. Good. So what's the effect? There is a popular joke about this. That guy, Kamil Ones, was one of the pioneers of really industrial approach to a physical experiment. he had to liquefy much of liquid gases. So there was a system of pumps which have been pumping for a couple of weeks. Then he got several hundred liters of liquid gases, and he had to make experiments very quickly. Otherwise, the stuff will evaporate soon. He doesn't have hands. He got to the streets of the city. He picked up kind of young and less responsible persons who've been hanging on streets. And for little money, he could run these experiments with the help of these guys. It appears to be that one guy was so irresponsible as to break expensive ohm meter in the course of experiment. So he has been sent away without paying. But then the professor decided to check ohm meter once again. He reproduced the same curve. He couldn't send away himself without paying. He had to think about the situation. That's how superconductivity has been discovered. So, abrupt change or disappearance of electrical resistivity at certain conditions, certain critical temperature. So below this temperature, we have very unusual material which does not resist electric current. It means that there are spontaneous currents in this material, which are property of the ground state, which are not dissipative. And it took only 50 years for very rapid development of physics to understand, after all, the macroscopic origin of superconductivity. Spontaneous currents was a key element. It appears to be that one of the most important symmetries, gauge symmetry, is broken in superconductors. Superconductors have phase as a result of spontaneous symmetry breaking, and this phase is responsible for these currents. That's at macroscopic levels. So all superconductors, they provide an example of macroscopic quantum states. In fact, they can be regarded as sources of quantum coherence. I will explain which type of coherence I mean. Right. If one looks a bit microscopically, that comes from well, it's a little bit explanation for kids, but okay, I don't have time to go deeper. Like electrons would like to form pairs, and these pairs kind of condensate into a Bose condensate, which has these coherent properties. In fact, everything is true except Cooper pairs. They don't exist except in the condensate. Fine. Okay, let's take this for granted. Let's see what we can do with this. In order to start, I would like to concentrate a bit on the spectrum of charge excitations in superconductors. Okay, simplest superconductor is a superconductor without superconductivity. It's normal metal. So let's sort charge excitations in normal metal. Right. In this case, we count all excitations from Fermi energy, right? And there are electron excitations. They come from the states which have energy above Fermi energy. One can also excite the states which are below Fermi energy. What are these excitations? Holes, precisely. In this case, the state is filled. To excite it, one takes electron away. There are hole excitations. So we conclude that the spectrum of excitations in normal metal consists of two branches of electrons and holes. Right. What happens in superconductor? In superconductor, we have condensate of Cooper pairs. Okay, good. At least condensate is a good thing. Condensate means that we have uncertain number of Cooper pairs. In this case, if the number is uncertain, it's like you know, a wallet with a big hole. You put money on that, and it doesn't stay in the wallet. Fortunately, this wallet has also unusual quantum mechanical property. One can also extract Cooper pairs from this wallet for free. Right. What would be consequence? One could take a hole and take a Cooper pair in from condensate, doesn't cost any dissipation, any energy, and it becomes an electron. One could take an electron and damp a Cooper pair in condensate. As a result, is a hole. It's a coherent process, and it means that electron and hole excitations in the presence of superconducting condensates are mixed. And in fact, the true excitation is neither electron nor hole. It's a superconducting quasi-particle, which is a linear superposition of electron and hole. Okay, perhaps you know if the levels cross, it's only possible if they don't talk to each other. If there is any overlap, any matrix element which connects these two levels, they repel from each other. It's called level repulsion. And superconducting energy spectrum is, in fact, manifestation of this level repulsion. So the fact is, in fact, gapped. It has finite energy gap, delta. Fine. Well, let us discuss analogies and difference between semiconductors and superconductors. What I've drawn here is a typical spectrum of a semiconductor, which is insulating at 0 temperatures. Okay? But we are talking about superconductors, so why don't we see insulation? Yeah, right. It means that the current in superconductors at low energies is not transferred by charge excitations. It is transferred by condensate. It's some property of condensate, superconducting current. Fine, very good. I promised to go to scattering, and I have little time, so let me go quickly. Oops, that was too quick. Yeah. So let us take normal metal on the left. So it has very distinct spectrum of either electrons or holes. Let me take ideal nanostructure which connects it to superconductor. Ideal in the sense that no scattering happens at the nanostructure. Adiabatic quantum point contact can be a good example. All right. Let us see. Let me take an electron in normal metal and direct it towards the superconductor. And let me take the situation when the energy of this electron is smaller than the energy of superconducting gap. So then we have very sharp situation for the gap. It cannot penetrate the superconductor. There are no states to go. it cannot get reflected because there's nothing which can reflect it at the interface. I don't know what I would do in this situation. I don't know what would you do in this situation.
Try again.
One cannot turn back. It's like you're in the car and there are no brakes. Stay means that there should be some obstacle, right? Try to stop the car without having any obstacle.
You push a pair. You push a pair.
Push. That's interesting. Never heard of pushing the pair. But in fact, something like that happens. The electron interacts with a pair in this condensate. Okay, one could, it's not very polite word, push. Okay, it interacts with the pair. And in this case, it is converted into Hall and finally can get back because velocities of the holes are different, are opposite. Good. This is a process which is called Andreev reflection. So there's a cartoon what happens. So there's an electron which goes to superconductor, and in fact, although you send single charge, double charge goes into superconductor. The Netherlands is a very convenient country for explaining Andreev reflection, like Russia was ideal country to describe a kind of interference between two tunnel barriers. So it's just a typical Dutch saying which you used to hear very often, now less often, twee halen, één betalen. Fine. You send one electron, you get the second one for free. Right. Indeed, one can run proof check and see that all basic conservation laws are fulfilled for this process. Energy of the hull is the same. Charge conservation, if one takes into account Cooper pair hulls. Momentum is conserved, so while despite the fact that hole goes in opposite direction, momentum is the same as in the beginning. Spin is conserved as well. The process, which is called Andreev reflection. Right. That one can understand without any quantum mechanics, just at the level of particles. If one tries to understand it on the wave, on the level of waves, if one looks at the wave functions, then one understands that it's a little bit like the spin, but without spin. Wave function of an electron close to superconductor or inside superconductor must have two components, electron component and hole component. Right? There is a wave Hamiltonian for these components. This is at the usual terms in the Hamiltonian which do not change electron to hole, hole to electron. They could describe potential scattering, everything which we know about the metal. And there is a superconductivity which mixes up electrons and holes. They are not coupled in normal metal, so these two types of waves could exist together. But let us consider a wave which starts in normal metal, gets to superconductor. Perhaps it experiences some scatterings there is a kind of like a scattering of the wave. Right. It gets to superconductor. It is converted to whole wave. But holes kind of, it's like electrons which live in opposite time direction. So upon the reflection, it does very interesting magics. It just follows precisely the electron trajectory. Like a magic mirror. If we had such magic mirrors for light, we could, they're very expensive, we could have such magic mirrors for light. In this case, we could see through mist with this mirror, with these mirrors. We could cancel effect of light scattering. Well, something like that can happen for electrons which experience Andreev reflection. So, two-component wave function. And there can be phase difference between electron wave and Hall wave, which will become important for me soon. Right. Let me, yeah?
I have a quick question.
Yeah?
Over here. Could you go back to slide 10 or first one? And then
Let's choose one slide or two slides.
concerning the process of time, how can we actually, I mean, is it reasonable to think about the whole only being excited as soon as the electron hits the interface? Because if we go back another slide now, the whole current over this interface is only conserved if I take hole and electron on one side as a current and the super current on the other side. I cannot think about the electron coming first because this is just like a current of one charge, and after that I would generate charge.
This question is not specific to superconductivity. Let us consider what, let us recall what I said about scattering states. In principle, it's a wave function, and it persists at any given moment of time. It has incoming wave and outgoing wave simultaneously.
Right.
From the other hand, it describes a classical process which would happen at some instant. So there is no problem with that. If you go from classical mechanics to wave mechanics, you have magic ability to describe it all in the same time moment. Right, and now we just have two-component wave functions, so we can describe this, this process of Andreev reflection in very same way as usual reflection. Yeah?
One question on this slide. It is almost conservation of momentum because if the energy is the same and then the velocity flips, this almost momentum conservation just means that over the sign of the momentum flips, or what do you mean here? There is almost.
I paid so much attention to momentum conservation because I could not transfer it to any obstacle. Usually it's no problem, right? But now I don't have obstacles, so the moment has to be the same. And indeed, the momentum of the hole is the same, although it moves in different direction. All right, where I'm supposed to be now? Let me talk about, let me add some more physics to Andreev reflection. So we really want to go to reflection setup. So we consider single channel, we consider plane wave, which comes from as an electron. It goes to superconductor. And if the energy is smaller than the gap energy, then one cannot really go to superconductors. So the wave function must vanish in superconductor. It happens at some distance, which for real situations can be eventually quite long, can be even microns in pure metals. It's superconducting coherence lines. Nevertheless, sooner or later, it will be converted into Hall at this distance and will return as a Hall. What will be important for me for concrete applications is that it acquires a phase. This phase consists of superconducting phase of this particular superconductor, and also there is energy dependence on this phase, on the energy on the gap scale. Let us talk about the situation when Andreev and normal reflection is combined. In this case, I just put a nanostructure which has some reflection coefficients. All right, let us see what I have. I still come with incident electron. You know, it has an amplitude to go back as an electron, and has an amplitude to be Andreev reflection. Okay, there is a single channel, and I understand that it's already almost the end of the lecture, and mentally you are at lunch. Nevertheless, let us try to concentrate, and let us express current in this channel through these amplitudes. Let me help you beat through current. Would be some current which comes from the number of electrons coming per second, this number of attempts. Then if it were normal structure, we would just put transmission coefficient. Okay? We have to put something now. And it has 3 terms.
The part of the electron that transmitted into the electron.
Mm-hmm.
Then we have to subtract the parts of the electron and get reflected into the hole.
Yeah, let's talk about normal reflection. I will give you that. If the reflection would have been only normal, we would put here a chance to be normally reflected. All right, that would give us transmission coefficient. I said there were 3 terms. Can you help me and add the third term?
There is the current of common phase. There are current of Cooper phase.
There is, but not in the normal metal we look at.
But current the same in all parts.
Yeah, so one has to know this current in one of the parts. Then one knows it in another part. Who will give me such a term?
The current of all.
Current of Hall? That's right, but I would like to have more mathematical expression. Yep. Fine. Here we are, 3 terms. Again, let me concentrate on this unusual discount which we can have in this Andreev shop. If Andreev reflection, probability of Andreev reflection is 1, okay, in this case this disappears, we have 2. We have doubling of electric current. Fine, let's see how much time do I have? 7 minutes. 7. Good. Then I want to go rather quickly. Andreev conductance. With the knowledge we have just acquired, this exercise is very similar to double barrier problem we have considered. We can now compute it with our hands. What do we have to take into account? All processes when electron comes to the barrier, penetrates the barrier, is Andreev reflected. Okay, that's the first possibility. There are more complex chances. It comes, penetrates the barrier, is reflected from superconductor, is reflected back, gets another Andreev reflection. There are processes, as we learn, one has to sum up amplitudes of all these processes. And that will finally give us amplitude of what? Which amplitude is drawn here? Yes, the amplitude of Andreev reflection, precisely. Right. Upon doing that, one should not forget about Andreev phase. So at each Andreev reflection, there is a phase factor accumulating. Right, that's what I do. So in fact, I again have to sum up geometric series. The phase accumulated by Andreev reflections enters expression. If energy is small, much smaller than 0, it's a very certain value. It's power 2. So one can write a simple formula, rather comprehensive formula. Small energy, electron enters transmission channel. What is the chance of Andreev reflection? It is directly expressed in terms of transmission coefficient. Yet another universality from quantum transport. Again, as I said, it's not important that anything consists of atoms. It could be any superconductor on the side. It could be a nanostructure from copper, wood, or whatever. It could be even bilayer graphene. In any case, the Andreev reflection chance is related to transmission coefficients for the structure. Fine. I don't think I have time to go through the examples. Let me just mention Joseph. I am very sorry. Right. Let me just mention that one can have supercurrents if one has two superconductors next to each other, connected by a nanostructure, and there's a phase difference. So this is called Josephson junction, Josephson effect. It is, simplest, it's a supercurrent in the world of nanostructures. Right. I don't think I have time. No. Okay. Let me just stop here. I think I'd better devote time to Josephson junctions than to talk about the topic of fourth lecture. Let me stop now, and now you have time for your question.
So in the previous slide, about the
You mean this slide? Okay.
So here you consider that the two interfaces are NS interfaces.
I see only one interface here, right? But it's an interface which might reflect electrons with a certain chance. So I model this interface with a scattering matrix which has transmission probability, reflection probability. And then I have a ideal Andreev interface. Does this answer your question? Good. Then I'm done.
Are there any other questions right now? If not, there is also a forum session tonight where you, if you have any other questions, you can always ask it. But for now, let's thank the speaker.
Thank you.